Hey, welcome to today's lecture. This is a lecture on direct use of the sun's energy for solar thermal energy, for solar heat, for heat. So we're going to use solar thermal energy, which we could use for making hot water, actually making steam, for distilling water, making pure fresh water, for cooking, for drying things like solar food dryers, for cooling and refrigeration, and in passive solar buildings. Fantastic book that was published in 1964, again pointing out the idea that there are no new ideas under the sun. There's this book by Farrington Daniels on direct use of the sun's energy. Still worth reading today. Another way we can use the sun's energy directly is with solar electricity. So solar thermal and solar electricity are the two big ways in which we can use the sun's energy directly. And we can use the sun's energy indirectly through wind power, which is solar energy but not directly from the sun, and also water power and biomass. But direct solar energy, solar thermal, and solar electric. So today we're going to talk about solar thermal. So here's a machine that was built for the Paris Exposition, which I think was in the late 1800s. And these giant machines pumped 500 gallons of water and even powered an ice maker. So they were able to make ice with solar energy in the 1800s. And here's a a unit that was collecting the sun's energy and making heat, the solar motor, and I guess it made steam and made an engine. It made a steam engine run. And notice that they say Pasadena electric cars passed the entrance. So I guess electric cars got in free. And here's a engraving of the world's first solar hot air engine. So this uses a Stirling cycle engine, which is an external combustion engine. Concentrates so the sun's rays come in perpendicular to the Earth's surface. They hit this shape, which is called a parabola. And the unique feature of a parabola is that no matter where the light rays hit, they're all concentrated to one point here. So it's a way of taking all the solar energy that is intercepted by the kind of mouth of this parabolic curve and concentrating it here. So there's this much solar energy across here hitting, but as you can see, it's all concentrated on that one point. And unique feature about a Stirling cycle engine is if you heat one end by concentrating the sun's rays on it, cool the other end just by having it in the atmosphere, the piston inside will start to move back and forth. You don't need to burn a fuel to run it. And here's an example of a modern version of this, where you've got something that looks a bit like like a satellite dish that collects solar energy. So all the solar energy that hits the surface of this mirror is reflected right here. And then you've got a little Stirling cycle engine, and that runs a generator and generates electricity. And something that looks like this has the record for the highest conversion of sunlight into electricity, even higher than photovoltaic cells. I think it's about 40 some odd percent of the solar energy collected here is actually turned into electricity. So there are three types of solar water heating collectors. They're the kind that just collect low temperature energy, medium temperature energy, and high temperature energy. So low temperature energy, why would you need that? Well, if you want to extend the season for your swimming pool, and you really only have to heat that water up to 80 degrees to be comfortable from 60 or 55 or something, then that's pretty easy to do with solar energy. And then you might also want to heat your hot tub or spa up to 100, 110. That's considered low temperature energy. Medium temperature energy is up to 180 degrees. And then with, going back to low temperature, these collectors, you don't even have to put glass on the top of them. They're just a mat, a plastic mat typically, that you lay out in the sun, and the sun hits the mat, and the water in it gets hot, and then you pump that hot water through your pool. Similar principle to if you ever had a garden hose that's laying on the ground on a sunny day and you turned it on, and the water can be so hot in that garden hose, especially if it's black, it will burn you. And so that's the principle here. You don't have any glass cover. It's just a black rubber mat that you can, with tubes in it that you can run water through. Then for medium temperature, that's up to 180 degrees. These are glazed, meaning they have glass over them, and then they're insulated. So these are for things like domestic hot water in your house, heating up your water tank in your house, laundries, things like that. And then very high temperatures, up to 500 degrees Fahrenheit. Then these are, you actually have to concentrate the sun's rays to get this kind of temperature. And that's used for industrial process heat, electrical production, if you want to make steam, that kind of thing. So here's a basic, what's called a flat plate solar collector. And it's a really simple device. It's just a box, so here's the box, and typically they're about 4 feet across this way, and 8 feet long. And it has a glass cover, and inside the glass cover there is a metal plate, and attached to the metal plate are copper pipes. So the water comes in at the bottom, and then it goes through the copper pipes and out at the top. And when you put this in the sun, the solar energy goes through the glass cover, hits the black metal plate, and inside here, because it's insulated, it heats up. And so it can get very hot in here, hot enough to boil the water in these tubes. Just think of how hot it gets in your car on a sunny day, even in the wintertime. You leave it in the parking lot, you go in shopping somewhere, you come out, and your inside of your car is just baking. So this is the same idea. It's also called the greenhouse effect, where the sun's rays easily pass through this glass, and then when they hit because they're very high temperature, high frequency waves from the sun, and when they hit this solar absorber plate, it's called, this metal plate, they turn into heat at maybe, instead of 5,000 degrees Fahrenheit, Celsius, they turn into maybe 100 degrees Celsius, and that's long frequency long wavelength radiation, which is reflected back by the glass. So the high temperature energy of the sun passes right through, but then when it turns into lower temperature heat, that gets trapped in here by the glass. The glass doesn't let that back out. And so that is essentially all a solar flat plate collector is. It's just a box, 4 by 8 foot typically, could be 4 by 10, different sizes. Insulated on the bottom and the sides so that you keep the heat in that you collect, and then some way to take the heat out through a fluid like water. And so the water comes in here, rises up through these pipes, gets hot, comes out here hot, and goes to your water tank. So here's a couple of flat plate collectors that used to heat the water at my house. And you can see the tube going in at the bottom. There's a tube coming out at the top. These are about 4 by 8 feet, and they provided plenty of hot water every sunny day. So again, here's a view of that, where you can see the glazing material that lets the light through, the absorber plate, the metal plate, the flow tubes where the water flows through, and the header at the top that collects the water from all the tubes so that it can flow out. So it flows into the tubes, comes up to the header pipe, and flows out. Here's the frame and the insulation. Put this all together in the system, what you'd have is you'd have a tank here. You'd have a little pump, and that pump would pump water from your tank up into the collector, flow through the collector, get hot, flow through the collector, flow out, and then back to your tank. And then the pump would continue that process, that loop. Now, you don't want the pump to run at night when there's no sun. You don't want the pump to run any time actually that the solar panel is colder than your tank, because you'd be actually cooling your tank then instead of heating it. So what this differential thermostat, DT stands for differential thermostat, is it's constantly monitoring the temperature of the solar panel and the temperature of the water in your tank. And whenever the temperature of the solar panel is hotter than the water in your tank, it turns the pump on. And so in this situation, which simplified situation I showed here, we're actually using the water in the tank to go up to the collector and to collect the energy. Now there's a problem in a freezing climate, because at nighttime, if there's water in these solar collectors, it'll freeze and they'll break. So in freezing climates, you need to do something different. And in freezing climates, what you do is you actually circulate antifreeze, like the fluid that's in the radiator of your car. You know, so it cools your engine, but it doesn't freeze in the wintertime because it's got a substance, typically some kind of alcohol, that freezes at a very low temperature, much lower than what you would normally see what you would see in the winter, not just normally, but you never see a temperature that cold in the winter, so it will never freeze. And so in this case, what you've got is the antifreeze solution is kept completely separate from the water in your tank. So the antifreeze solution goes into your tank into a series of coils, okay, and then those coils get hot because the antifreeze is hot, and then those coils are sitting in your water tank, so they're surrounded by the cooler water, so they heat the water. So in this case, what happens is that you'd have a pump here, and you'd be taking the cooler water from the tank, from where the fluid has given up its heat to your tank, so it's cooler, and it goes up to the solar collector, goes through the collector, gets hot, and then comes back down here hot, and then goes into your tank through this coil of tubing, coil of pipe, and because the pipe is in contact with the water, it's under the water in your tank, then it gives up its heat to the tank. Now, these systems work really well. Here's another system, which is called drain back. And again, this kind of system, you wouldn't necessarily have to use antifreeze. And the way this works is that So what happens here is that your pump comes on and it pumps the fluid up around here. And then when it comes back, it goes into this tank. And when the pump shuts off, all the fluid drains out of the collector and drains out of the pipes, so that there's only fluid in the collector when the pump is running. And the pump is only running when the collector is hot, so it won't freeze. If the collector is cold, the pump shuts off, and the fluid will just drain back to this tank. It drains back to this tank, and it drains out of the collector. Okay. We won't get into this. Don't worry about this. Well, I'll just mention this because, excuse me, you can have one tank system. Excuse me. You have one tank systems, which means you just have one tank that the solar hot water heater, the solar hot water system heats, and it's got a heat exchanger in it. This device is called a heat exchanger, and it's just essentially a coil of pipe that you can run a fluid through, and a hot fluid through from the collector, and heats up the water. Now the problem with this tank is that let's say that you get up in the morning and you take a shower and the sun hasn't come out yet, and you use up all the hot water in this tank. It's got a backup element. It's got a backup heating element. And if you use up all the hot water in the tank, that backup heating element will come on and heat the tank up. And then by the time the sun comes out, the tank is already hot. So sometimes these aren't as effective as a two-tank system. So how the two-tank system works is you've got one tank that doesn't have any heating element in it at all, and it is heated by the solar collector. And then the cold water comes in. Cold water comes into this tank, from the cold water supply to the tank. And then if you draw hot water, there's actually two tanks here. So if you draw hot water here out of this tank, what it does is it then draws its intake from the hot water output of the first tank. So if this water is always hot from the solar, then when you draw hot water from the first tank, its supply comes from the hot water of the solar tank. So that this tank is never cold if the solar is working properly and if there's plenty of sun. But if the sun, if you use a lot of hot water or the sun is not strong for a few days, then these elements will come on and heat up the water. And these backup electric elements would come on and heat up the water. But in the situation where you take a bunch of showers and you are using up all the hot water, what's going to happen then is this is going to be full of cold water. This will have hot water that will be heated by these elements, but then you'll still be able to heat up this full tank of hot water here. There'll be cold water here that you can heat up, if that makes went through that kind of quickly, but it's not a huge single tank systems. It turns out, even though it sounds like that's a disadvantage, they work just fine. 2-tank systems are a little better. And here's a guy in Fairfield who built one of the first solar hot water systems in Fairfield. His name is Roy Tonneson, and he wrote about the system in Home Power magazine. Here he is right here in Home Power magazine. And solar hot water was the first commercially viable, cost-effective way to use solar energy. Until just the last couple of years, it was always the most energy you could get per dollar to solar. The recent drop in solar electric prices have really changed that a little bit. And because solar hot water system, solar hot water collectors, these flat plate collectors, are really fairly simple device, they can and have been built in shops and backyards all over the United States. And I'll show you some that were built here in Fairfield. This is a guy named Roy Tonneson who lives in Fairfield. This is his solar hot water system. And we won't bother to go into the details of it. And here it is outside his house here in Fairfield. You'll still see that. I think, it's on 15 or 20 years now that it's been heating all of his hot water. During the year 2000, they turned off the natural gas water heater for 9 months. From mid-February to mid-November, we got all of our domestic hot water during that time. Then in non-freezing climates, you can actually build really simple solar hot water systems. So all you really need to do in a lot of cases is just take a black metal tank and stick it in the sun, and that'll give you, every sunny day, that'll give you several very hot showers. If you want to go a little further than that, you can take that tank, put it in an insulated box, and put a glass cover on it, and then that will produce lots and lots of hot water. So you don't need a fancy solar collector or a separate storage tank. The collector and the storage tank are all in one. Sometimes this is called integrated collector and storage, or ICS. And here's an example of one right here, where you've got a tank here. Maybe it's an old hot water heater tank you get from the junkyard, and you put it in a metal in a glass insulated box. And I'll show you some I've built in Hawaii. Now, another thing you can do in cold climates, if you put because warmer fluids are lighter than colder fluids, they will float to the top of a colder fluid. So if you have a tank of water and it's cold water and you introduce hot water into it, the hot water will actually rise and float on the top of the cold water. And you can use that fact to actually pump the water, move the water in your solar hot water system. So in this case, the collector is lower than the storage tank. And what's going to happen is cold water is going to sink to the bottom of the storage tank. And then it's going to sink down here to the bottom of the collector. Now the collector is in the sun, the water in there is getting hot, that water is less dense, it's lighter, it's going to float up here to the top of the storage tank. And as it floats up to the top of the storage tank, it's actually pushing out the cold water, which is heavier, and it's going to sink, and it pumps itself. This is called a thermosiphon system, and it really only works well in non-freezing climates because you have to have the water, you have to circulate the water from the storage tank through this system. Now here's a simple system that I built in Hawaii. This is my property in Hawaii, where we just took a 55-gallon drum and 2 old solar hot water collectors that I got for free, and just plumbed it up so that the bottom of the tank is connected to the bottom of these collectors, and the top of the tank, the top of the collectors go off to the top of the tank, and this would make enough hot water for several, 4 or 5, maybe 8, 10 showers, depending on what time of day you started taking the showers. Take them early in the day, like in the afternoon. It has time to heat up several times during the day. And here's another example of one. Here's an example of a commercial unit. Now, another thing you can do is you could take, you think about where could I find a metal insulated box that I could put a tank in, and if an old refrigerator fits that bill really well. And so I made several of these collectors. Here's one in Hawaii made from an old refrigerator with a glass cover over the fridge, and an old water heater tank that I got from the dump. So I built all this thing mostly, except I think I had to buy the glass in this case from recycled materials. And then you can see here that on an 82-degree day, by noontime, the water temperature in the tank was already 106 degrees, which isn't steaming hot, but it's a nice on a warm day. It's nice, really comfortable temperature for a shower. And we would get, sometimes a dozen showers out of this system. And here's one that was built at the Eco Village by students who lived at the Eco Village property during the first years of its development. Let's get through this. Here's a really huge, so really people have built really huge solar hot water systems. This is Packerland Solar. It's a meat packing plant, and they needed huge amounts of hot water for their meat packing plant, and they put in 5,000 4x8 foot collectors, huge amount of collectors. More than 215 kilometers of steel and copper pipes. And they actually put too many solar collectors in, and the system got too hot, and they sold a bunch. And the ones you saw earlier that were at my house in Iowa actually came from this plant. They were taken down from this plant and sold used solar collectors. Here they are right here. Those are from the Packerland Solar plant right there. And let's talk a little bit about the theoretical maximum efficiency you can get from a solar hot water collector. So here's a slice through a solar hot water collector, and here you see the insulation, you see the glass, you see the absorber plate, and you see the tubes. And so if you look at the energy balance, remember, energy is neither created nor destroyed, so all the energy that comes into the system has to go out. Any energy that's leaving the system will have had to come in at some point. And so in this case, what happens is the sun's energy is coming. Some of it bounces off reflects off the glass, and so some solar collectors use special non-reflective glass. And then some of the solar energy goes through the glass, goes in and hits the absorber plate and heats up the absorber plate. So then what's going to happen is some of that heat is going to be lost out through the glass, and even though it's insulated, some of the heat will leak out of more of it will leak out through the glass because there's no insulation here, and a smaller amount of heat will leak out through the insulation in the sides of the tank, and then some of the heat will be delivered by hot water. Okay. Now, so you can't ever get all of the solar energy that comes in out unless you're collecting the hot water at the same temperature as it is outside. So if you want 70-degree hot water, if it's 70 degrees out, then you can get a lot of that water without any losses because it's the same temperature outside as the water you're collecting. But if you want to collect, let's say 140-degree water, then what's going to happen is it's going to be 150 degrees, let's say here, to enable you to get 140-degree water. It's 70 degrees outside, so heat flows from warm to cold. Heat's going to be flowing out of this system. And all the heat that flows out of the system is heat that you can't take out in hot water. So the more the losses are in this collector, the less is available to go to the hot water for your tank. And so that's why you want to put insulation in. That slows the heat loss. Maybe you even want to insulate the sides. Sometimes you use 2 layers of glass to provide more insulation for the glass part of it. And then the other thing that changes here is the ambient temperature. So as it gets colder, let's say that you always want to collect temperature, you always want to collect the water at 140 degrees. So in here it's always going to be 140 degrees. And then the outside temperature, let's say it's at 70 and it starts to drop. So what's going to happen is as the outside temperature gets colder and colder, more and more energy is going to be lost through the collector, out of the collector. There's only a certain amount of solar energy coming in. So if more energy is being lost as the temperature drops through the collector, then there's going to be less energy that's delivered to the hot water. There's going to be some point as the temperature drops outside, it gets colder and colder and colder, and you're trying to maintain your 140 degrees in here, where all the solar energy coming in is actually going to be lost as waste heat here, as heat through it's leaking out through the collector, and there will be no more to put in the hot water. So every solar hot water system has a minimum temperature which it can start to operate, even on a sunny day. And so let's take a look at what some of those are. So in this case, so here's a swimming pool collector, that has no glass on it. It's just a absorber plate. Typically, it's a rubber absorber plate with little rubber tubes manufactured into it that you can flow water through. And when the sun shines on it, it gets hot. But it only has to get to 80 degrees. So if it's 80 degrees out or 90 degrees out, even without glass, this doesn't lose very much energy. Let's say that it's 70 degrees out, and no, let's say that it's 90 degrees out, and you want to get 80-degree water out of this thing. Well, you can actually, or that your swimming pool is 80 degrees, so it's holding the temperature as you run the swimming pool water here. This is holding this at 80 degrees. And it's 90 degrees outside, and the sun is shining. You can actually get more than 100% efficiency because you'll get all the solar energy plus some of the 90-degree heat from the atmosphere will leak into this 80-degree water that you want to warm up. So swimming pool collectors, because they operate at very low temperatures, and typically in the summertime when the temperature is high, can actually operate very efficiently even though they don't have any insulation or glazing on them. If you were to try to get high temperature heat out of this, like try to collect the energy out of this at 140 degrees, you'd lose a tremendous amount of energy, and it wouldn't be able to operate at a very low temperature. Now, let's take a look at, here's an unglazed swimming pool heater. You notice it starts at a very high, this is the efficiency. So it starts at a very high efficiency, but then as the temperature difference between the swimming pool collector and the atmosphere gets higher, that's what this is the temperature difference, then this becomes a point where at this temperature difference, then all the solar energy is being lost and you can't collect any, so the efficiency is zero. Now if you put glass over it and insulate it, like this one, single glazed domestic hot water, DHW means domestic hot water, then what you're doing is it's actually a little less efficient because you're blocking some of the sunlight with this glass when the temperature difference is really low. But at temperature differences where you typically want to collect energy, maybe 100-degree temperature difference to collect for your domestic hot water for your house, then it can actually have a much higher temperature difference between the collector and the outside temperature than an uninsulated panel. And still, at some point though, it gets to 0% efficiency. And that's when it's cold enough outside so that all the incoming energy is being lost through the collector and there's none left to go into the water. And then if you put 2 layers of glazing, you can extend this out even further so that it can collect energy even as the temperature gets lower or at higher temperatures, higher temperature differentials between the temperature of the atmosphere and the temperature inside the collector. We've talked, there's actually several different kinds of sunlight, and there's direct sunlight that you get, when on a clear day and you get that, feel that warmth on the side of your face, and that's called direct solar energy. But then there's also diffuse solar energy that's reflected off the clouds. That's the kind of solar energy you get on a cloudy day. So solar hot water panels, solar electric panels, they actually work on cloudy days as well. And then you get some energy that's reflected off the ground, reflected off things around. So if you look at, for example, a south-facing wall of a building, the direct energy it's getting might be 485 BTUs, but the diffuse energy that's hitting it because of clouds and other things, ways in which the atmosphere diffuses the solar energy, might be almost half as much, and then the reflected energy is this much. So that gives you an idea of especially if this ground is covered with snow and it's white, it can reflect quite a lot of energy onto a solar panel or a solar collector. This is a special type of solar collection device called an evacuated tube, and this is designed so that it can operate at very low temperatures outside and still collect useful energy, because essentially this is like a thermos bottle, a glass thermos bottle. So there's an absorber plate inside, and there's a round tube of glass. There's an absorber plate inside, but then all the air is drawn out, a vacuum is drawn in this glass tube, so that any energy that gets in, it's very difficult to get out. Just like in a thermos, where you take a thermos bottle and fill it full of hot water, the next day it's so hot because the rate of energy flowing out of that thermos bottle is so well insulated because of the vacuum around it. And so what happens here is that you've got these tubes, and then you've got what's called a heat pipe. It's just a fluid that boils, and then it rises, and then where you have cold water flowing by the end of this evacuated tube, the cold water condenses the fluid. It could be something like alcohol, and that gives up a tremendous amount of heat. When something goes from a gas to a liquid, it condenses, and then it drips back down here, and when it gets hot in the collector, it boils again. And so it just does that all day long, and that transfers the solar energy to the water up here in this what's called header pipe. Here's we use evacuated tubes in the Sustainable Living Center. Here's another diagram which shows the evacuated tube, where it's called evacuated because there's a vacuum drawn. There's a copper pipe in the middle of it, and there's a liquid in here that when it gets hot it boils, and then it comes up here where it's outside the tube, and you run water by this little bulb here, and that cools it, and it condenses, and it drips back down. Just does that all day long. And these are fairly high-tech devices to make. You can't really make them in your backyard, but they're made by the tens of millions, maybe even hundreds of millions in China. In some cities, there's hundreds of thousands of people, and all they do is make these, and they're all over China. And then they've become very popular in the United States. We have some on the top of the Sustainable Living Center roof. This is the Sustainable Living Center under construction. And they continue to collect solar energy at very low temperatures, even in the wintertime. And they can make very hot water too. So you can see here, somebody's taking one of these evacuated tubes and actually plugging it in to this header pipe so that it can collect solar energy. And you can see over here, here's the cold water coming in. The cold water will go across here, pick up heat from these evacuated tubes, and then bring it back to the tank. Let's not talk about that. So here's a swimming pool collector, typical swimming pool collector. Again, it's just a flat plastic mat that is laid, on a roof or even on the ground next to the swimming pool. You can make these quite large because swimming pools, even though you're not raising the temperature of the water very much, it's a lot of water, and they're fairly inexpensive. Mounting solar collectors, I think we'll skip through this. You can mount them on the ground, you can mount them on roofs. Pricing. Typical solar hot water system costs between $125 and $175 per square foot, and you'll need between maybe 60 to 90 square feet to heat the water for a house. Here's a rule of thumb for how to design solar hot water, how to size it. When you're trying to remember when we talked about, okay, how do you match a renewable energy source to a load that you want to cover by that renewable energy. And the first thing you do is you estimate the load. So the load in this case would be 20 gallons of hot water per person per day. So if you got 4 people, that would be 80 gallons of hot water per person per day. And the collector sizing, you could start with a rule of thumb collector sizing of 1 square foot of collector per gallon of hot water needed. So if you needed 80 gallons of hot water, you'd need 80 square feet of collector. And collectors don't come in just any size you want. You can get them typically 3 by 6 feet, 4 by 8 feet, 4 by 10, 4 by 12. 4 by 12 typically are pretty big and heavy because you got a piece of glass that's 12 feet long. I like size 4 by 8, 4 by 10. And so 4 by 8 is 32 square feet. So if you needed 80 square feet to heat 80 gallons of hot water per person per day, this is 36. You'd need three of those collectors would do it. And then for the amount of storage you need 1 to 2 gallons of storage for each square foot of collector. So then if you had 80 square feet of collector, you would need 80 to 160 gallons of storage. So it's 1 gallon per square foot of collector in a colder area and 2 gallons per square foot of collector in a warmer area. And again, tanks don't come in every size, but typical size tanks are 50, 80, and 120 gallons. And the cost typically is $125 to $175 per square foot of collector complete system installation. And often there are incentives available from government agencies and utilities to offset the cost. In Hawaii, every new home is required to have solar hot water. And here's some of the solar hot water systems at Abundance Eco Village. You can see these are flat plate collectors. These are evacuated tubes. And this house actually has more collector than you need to heat the water for this house. And the extra hot water is used in the spring and fall to run through tubes in the floor to heat the house. So this provides both space heating and hot water heating for showers and washing dishes and clothes and stuff. Here's a system that we put in Alaska with a group of students. This is Troy Van Beek up here, Robbie Gongwer, and these are solar hot water collectors that we installed in off Juneau, Alaska. Here it is. You can see the ocean out there. And you can use these, you can design buildings so that they just, by their form and their orientation, they collect and store solar energy so that the whole building is like a solar collector. But we're going to talk about things you can sort of add to buildings to help heat them, what are called active solar. The process of designing a building so that the building itself is the solar collector, that's called passive solar, because typically the energy doesn't have to be moved anywhere. The whole house is the solar collector. Active solar is solar you typically tack onto a house after you've designed it, and that solar is then it can be used, the solar heat that's being collected by this collector can be used in the house, but it needs to be pumped and moved around. And so these are called active solar systems. So there's passive solar and active solar. And here's in Fairfield Glass, you can see this is actually a little this is a little active solar hot air collector. And so this is a little glass insulated box that's put over the wall of this building, and then a little hole is cut in, some holes are cut in the bottom and holes are cut in the top. And in the wintertime when they want to get heat in here, then they just run a little fan, and the sun shines into this box and heats up, and then the fan blows the cooler air from the building into here, it heats up, and then it comes out the top and warms the building. And here's another active system for an underground house in Fairfield, and you can see these are a variety of different kinds of used solar hot water collectors, and then they run into tubes in the floor in this underground building, this house that's actually built into the ground. And underground houses are very well insulated, and so these solar collectors then take the sun's heat and pump them into the floor of the building. There's typically plastic tubes in the floor that the solar hot water circulates through. And we have a system like that in the Sustainable Living Center. Here's Kevin Hopp, very proud of his solar hot water system. He's a plumber in town who used to install all of the solar hot water systems. Okay, and this is the Christofiaks, Diana Christofiak, who used to work in the Sustainable Living Department, and her husband. They built this huge solar collector that's about, 30 feet long and about 8 or 10 feet high, and it heats almost all their hot water all year long. So they actually don't have to run a hot water heater even in the wintertime on cloudy days. This is so big. And then they have a tank in their basement, a 300-gallon tank. And this whole collector was actually built by MUM students out of materials that you can buy from a building supply store like Home Depot or Menards. So this is just standard copper pipe and lumber and insulation and various other things, and it works really, really well. And it was built for a very reasonable price, and it's a really nice job by Diana and Tom did building this. There's an article in your reading that describes how this whole system was built and works. And here's my old house. I had a very simple solar hot air collector, so I just this was built on site. And this is a metal roof, and then we built a frame on the metal roof, in which we could attach a plastic glazing material that the sun would shine through. So it's about 4 inches, like a 2x4 width, off the roof, and then the sun shines through here and heats up. And even on on this day, it had snowed, and it hadn't been the sun hadn't come out long enough for the snow to melt off the roof yet, so we weren't collecting energy yet then. But on another day, it was 5 degrees outside. You see this, and it was 96 degrees in the collector. So this collector was enough so that every sunny day I never had to use any other heating system. So I didn't have to use my wood stove on sunny days. And there's a lot of sunny days in the winter, so this worked really, really well. This is the systems at the Sustainable Living Center, where we've got these evacuated tube collectors. We've got a solar thermal storage unit, and then we take the heat out of the solar thermal storage unit, 5,000 gallons of water, into the floor. For every 5,000 gallons of water, we can, every 1 degree Fahrenheit we raise that water, it stores 41,000 BTUs. And on a very cold day, 2 degrees of heating this up 2 degrees and storing 80,000 BTUs is enough to heat the building for an hour. That one. So there are systems that we talked about this once before in the class. This is a system that actually was built in 1939, 100% solar heated, and it takes energy, annual cycle system. So it takes extra solar energy that's available in the summertime and stores it for use in the winter in this huge tank underneath the building. So this building could be 100% solar heated in 1939, even in a climate like Boston, by taking some of the energy from the summer and storing it in this tank and making it available for use in the winter. And this idea is been updated. This is a system that's been popularized by a designer from Wisconsin, and it uses it puts pipe underneath the building in sand, maybe 3 or 4 feet underneath the building, and then in the fall they start pumping heat into this sand, and it takes a month or two to heat this whole block of sand up in the fall. And then so you're taking that heat from late fall when you don't really need it to heat your house yet, and you're storing it and making it available even several months later. And this kind of district heating for solar, this idea of taking solar hot water and making it available to a whole bunch of homes. Here's a system. This is a centralized system that collects solar energy and delivers it to all these different homes. And here's one huge one that was built in 1985, actually. 10,000 square meters of solar hot water. And here's another district heating system. And I think they also even have a biomass plant. So in the wintertime when it's cold, then they can supplement the heat from the solar hot water collection system with biomass. And in the summertime they can not have to burn any biomass because they've got plenty of solar energy. And so in places like Sweden, what they do is, we talked about net billing electrical energy, where we've got electrical energy flowing into, you know, in and out of a house. You can have thermal energy, so you can actually have a hot water pipe coming into your house, and there's a meter on that hot water pipe, and you could actually pump hot water back out to the system as well. And there are now large-scale systems that allow you to store extra solar energy in the summertime in places like far northern climates like Denmark and Sweden, Norway, where the sun hours are very long in the summertime. In fact, the sun barely sets in the middle of the summer, and the days are very short in the winter. You can take that extra solar energy from the summer, store it in large tanks of water, or actually store it even in the ground, and then take that heat back out in the middle of the winter when you need it. And here's a district solar heating system that has a biomass plant right next to it. Another one. Another large solar hot water system in Norway, Sweden. And concentrating collectors, we talked about those a little bit, where we concentrate the sun's rays, so all the solar energy that hits this surface, this parabolic surface, is reflected onto this pipe. So there's this creates a line of solar energy that's reflected onto this pipe. In this case, you've got mirrors that reflect the sun's energy all onto a spot on the top of this tower. It gets very, very hot and can make steam. And let's see, here's one that's been in operation since the 1980s, a huge one, 50 miles east of Los Angeles, and it produced, let's see, 150 megawatts, 5 times 30 megawatts, so really huge. And we didn't make solar power plants this big again until for another 20 years, but this one's been operating for, we think, okay, when are we going to have big solar power plants? Well, they're certainly starting to be built now, but we actually have them that have been operating since the 1980s. It's just not very commonly known. Operating reliably, I would say, as well. And here's one from the early 1900s in Egypt, and the heat from this one, so this is a parabolic mirror, focuses all its energy onto a pipe here. And that energy then was used to pump water. It would make steam, run a steam engine, and pump water in Egypt. And these are here. We'll look at one other system, and this is an interesting system that is actually a pilot project was made in Spain. And what this is, it's like a huge greenhouse in the desert. So this is like a huge greenhouse structure. So the sun comes in here, it gets really hot, and it's all, the top of this greenhouse slopes up to this chimney. So when it gets really hot, all that hot air rushes here and rushes out through this chimney, and there's actually a wind turbine here, and it creates a really strong wind. So let's take a look at how that works.
When Don Quixote and Sancho Panza set off on their travels, they left from this part of Spain, the plains of La Mancha, about 150 kilometers south of Madrid. It's beautiful, rolling countryside, which is used now for farming wheat and growing grapes and olives. But there's something else in the plains now, which, if Don Quixote could return, he'd almost certainly want to joust with.
It's an extraordinary power plant which produces electricity economically simply from hot air. The project was commissioned by the West German Ministry of Research and Technology and built in Spain by the German civil engineers Schlag and Partners. Its design relies on one of the most basic principles, that hot air rises. As the sun heats up the air underneath the collection area, the air seeks and finds the only way upwards and out, through the chimney. And as it does so, it turns a turbine to generate electricity. Simple, but extremely effective.
Well, this is what the underneath side of the collector area looks like. 4.4 hectares of plastic material called Tetla, polyvinyl fluoride, which is held in position here by these spreaders like that. You can see them underneath here, pulled down by this heavy weight. And that's to keep everything tight so that it can handle the high winds that are generated, not only by the air flowing through to the chimney, but also in this area generally, winds can get up to around 150 kilometers an hour. During the day, the heat builds up here to around 50 degrees centigrade, and the air starts flowing in continually towards the chimney. But the interesting thing is that it also works at night as well as day, and in cloudy and rainy spells as well, because not only the air, but the ground beneath it is heated up during the day to such a degree that in the nighttime it re-radiates that heat back again, keeping the air warm and flowing inwards towards the chimney all the time. The actual plastic itself is only 0.1 of a millimeter thick, but it's very strong, and although it transmits infrared radiation, it's quite resistant to ultraviolet light, which tends to degrade plastic. And the life of sheets of plastic like this is expected to be about 10 or 12 years. One other quite important point that came out during the initial research program that surprised the builders of the chimney was that instead of a desert developing underneath this collecting area because of the high temperatures here, they got instead quite luxuriant plant growth underneath because of the greenhouse effect, which produced large quantities of condensation during the night. Well, this is the funnel, as it's known, and it's not much more really than two curved capes made of a polymer-coated fabric, which gives a smooth transition for the air that's coming in from the collecting area outside and going up into the chimney above me here, where you can just see the blades of the turbine turning slowly around. Well, it's switched off at the moment because they're making some adjustments. So if we step in here, you can get a good look up the chimney and see what it's like. And you can see that it's really not much more than just a hollow tube, some 200 meters high and 10 meters in diameter. And in here is the turbine. And it's supported quite independently of the rest of the chimney on this big steel tower here, about 9 meters above me.
The four blades can be adjusted while the turbine is running to maintain a constant speed, or an optimum one of about 36 kilometers an hour. This pilot one has generated a maximum of 60 kilowatts, but over a test period it averaged about 30 kilowatts of power output. Not a huge amount, but despite its size, the solar chimney was built in Spain for not much more than $1 million US, which means that even the pilot plant is considered an economic proposition. But what the experimental programs run so far seem to indicate is that the bigger the chimney, that is, the higher it is and also the wider the diameter, the greater the efficiency and also the higher the power output it can generate.
This solar chimney in Spain has demonstrated that it will be possible in the future to compete on a dollar-for-dollar basis with virtually any other form of power generation, with that one unbeatable advantage that it's got an inexhaustible source of free original energy in the sun.
So again, I just wanted to, we'll skip through the rest of this, but the idea I'm trying to give you here is that there's many different ways in which we can, make use of that solar energy as it comes from that super high quality, hot concentrated form from the sun, and then gets dispersed on the earth through, the solar thermal, wind, all these different things. There's just an endless number of ways in which we're just beginning now to unfold all the different ways in which we can use solar energy. Oh, let's talk about solar cooking just quickly, just so you can see some. Here's a solar cooking system that I use at my house. I really like this one. We can use it. I've got it at school, and we can hook it up, and you can play with it if you like. Cooks very quickly, and it's a real pleasure to use. It has to be aimed a little bit closer to the sun because it concentrates the sun's rays rather than some of the systems that don't concentrate the sun's rays, that don't have to be faced so directly to the sun. And here's, you can see the resemblance of these two solar collecting devices. This one from 1882. Here's a very simple, large solar cooker at Dancing Rabbit Eco Village in Missouri, and it's just an insulated box down here, and with extra and a glass cover with extra covers that extra reflectors that collect extra solar energy and reflect it inside the oven. And then on the back of the oven is where you open it up and put the food in. There's a little door in the back. And here's a very large version of that. We have one of these in the classroom that you're welcome to come cook your lunch in one day. Here's a very large version of that, which you could even cook a small pig, or maybe I think it can cook 50 loaves of bread at a time. It's called the Villager. It's designed to be used to cook in a village in a remote location. Here's a group of students at on a field trip using the solar oven here. And you can use solar water. You can use solar energy to purify and distill water. So here, this system was designed for pilots that have to bail out over the water when their planes crash, and they can inflate this little cone device, and the sun shines in here, evaporates the water, and then the water drips on this cone and is collected and can be drunk. And you can actually, so to distill water, it actually takes a lot of energy. Remember we talked about when you change the phase of something like water from a liquid to a gas, when you boil it, then and distill it, it takes a lot of energy to do that. But just to heat the water up without boiling it, it doesn't take as much. And it turns out that you can purify water through pasteurization, which means you just raise it to a certain temperature and hold it at that temperature for a certain time, and it'll kill all the living organisms in it. And actually, around 140, 150 degrees, 150 degrees, even for 2 or 3 minutes at 150 degrees, it'll kill any living, disease-causing organism in that water. So you can pasteurize water or you can distill it. Here's a typical box solar still, looking at a cross-section of it where you've got a sloping glass cover. You've got water in the bottom of the box. The solar energy comes in and evaporates the water. The glass cover is cooler because it's cooled by the atmosphere. The water condenses and drips down here and is collected in this drain tube for drinking water. And there's been, remote Greek islands where all the water supply comes from the ocean through solar distillation like this. And here's one that I built and used for a while. And again, you can see this bottom part is where you have the water that you want purified. It evaporates, it condenses on this glass cover, and then drips down and comes out into this bucket. And it's just a bigger one. We don't need to look at those. Salt gradient ponds, I think I'm going to leave that off, the discussion of that off. I think I'll talk about that in class a little bit. It's a very interesting idea, very super low cost way to collect solar energy, large amounts of solar energy. And that's it.